Hey guys, welcome back to Genius Learning. Okay, so from the last video, remember we have free charge on the outside and the density. So this just shows two different versions of that. So from the last video, this is just shrunk down. Here we have rho naught as our constant density, and these are all the values that we found from the last video. So we had electric displacement, electric field, total energy, and the last thing we found, which I put in purple, polarization. So we needed polarization in order to find the total bound volume. So our bound volume charge is found by using this equation, which we needed polarization. So now that we have it, let's plug it in. So we do the gradient, and in the radial direction, we're only left with, we're gonna have the bound volume charge is gonna be equal to -1/r², partial r squared on the outside, and then on the inside, let me see if I do a different color. We have all of this, right? So we're gonna have rho naught r/3 ke -1/ke, okay, and r hat and the r hat become 1. So we're gonna combine these two r's and everything else can come out. So let's see, we got the volume density. It's ugly, bro. Okay, volume density is gonna be, let's keep this 1/r² out here, and we're gonna combine these two and pull everything else out. So we got rho naught over 3 ke -1/ke, and then inside here we do the partial with respect to r to the third. All right, so we combine those two. So the derivative of this, all right, it's gonna be 3r². And if you see, this is on the top, the 3 is on the bottom, cancels with this one, and the r² on top cancels with this r² on the bottom here. So what we're left with for the bound volume charge is gonna be negative rho naught, free charge, and ke -1/ke, which tells us stuff about how the electric properties behave inside the material. All right, so now let's find the total bound volume charge. So remember, when you see total, remember that you're gonna have to integrate, okay? And so this is not the final answer. This will tell you the volume bound charges, but specifically in a certain location, we're not interested in. We want the entire thing, the total. So we're gonna use, let's see, I'm just gonna write it here. So we're gonna use Q is equal to the volume integral of the bound charge d tau, so the volume. So we're going to use this equation here to find the total. This is for the total. Okay, and let's plug things in. Let's see, let me do this in blue. Okay, we're going to do Q is going to equal, and that's for total, so I'm not going to label it, but we know what it's for. We're going to have 3 integrals, 0 to 2 pi, 0 to pi, and then this one is going to be 0 to a. This tells us that now we're going to have the total bound volume charge, because before this is not indicating the entirety of the space. So now we're integrating it over it, and we have the volume bound charge, and then the Jacobian r² sine theta dr d theta d phi. Okay, so solving this integral. So for lack of room, I'm going to skip some of the integral, but it's just going to be a little piece of it. So this right here, none of this we're going to integrate over. So we're going to take that out of the integral, right? And we're going to get 4 pi for the solid angle. We have the density bound, the volume bound, pulling it out, and then the only thing we're going to have left is the integral from 0 to a of r squared dr. Okay, so once we evaluate this, we're going to get r to the third over 3, and we're going to replace that with a. So the whole thing is going to look like q total. It's going to equal negative, because we have the negative here. We got rho naught. We got ke minus 1 over ke. And then from the integral, we have a 4 pi. And then what we pulled out of the integral is 4 pi. What we get from this piece here is going to be a to the third over 3. So we're going to get a to the third over 3. And this looks a lot like volume here. And so it's no coincidence that we have Q equaling rho, and what is expressed with rho is the dielectric constant. So now we're in a material, we just can't talk about the density without explaining how it moves through the dielectric and then the volume. So now we're talking about the total. So this is the total bound charge. Okay, now let's find the next thing on the list. All right, so what's the next question? Now we have the potential. Okay, so let's look at what we have for potential. So let's see. The question is, find the potential due to the system for all r's. So find the potential at all r's, right, for the system. Okay, so let's start off with the equation for potential. Okay, so we have, let me put it up here. So the potential is going to be equal to negative. This should be final minus initial. Final minus initial. Initially you started at infinity, and final you're going to go to some value r. Okay, so this is just a general expression for now. And then we have E dotted with dl. Okay, we're going to change this equation just a little bit, and specifically we're going to change the E. So we know that E is the electric displacement over epsilon. So let's change what's inside there. We got negative infinity to r, and in here we're going to have electric displacement over epsilon dl. Okay, so that's how we want to solve it. Okay, we have an expression that has the properties of the dielectric, and now we're going to need one more thing. We're going to need the Gauss's law to find the dielectric displacement. So we're also going to need 2 integral electric displacement dotted with differential area equals Q free enclosed. Okay, so these are all just the equations we're going to need. And we're also going to need Q, right? Because now we have to find Q. We're going to need the volume integral of the bound charge, and this is d tau. And let's see, so we have the susceptibility, right? This is the absolute permittivity. We need to express it in permittivity of the dielectric constant, and we know that the dielectric constant is 1 plus the susceptibility, electric susceptibility. Okay, so these are just the equations we're going to need for the next following steps, which is to find the potential at all R's. Okay, so keep in mind that chi E is equal to 0 if you're outside the dielectric, or you are in a vacuum. Okay, so there's no effect if you're outside of the dielectric. So then chi would be equal to 0, making Ke equal to 1. All right, so that would make this equal to 1. So just keep that in mind. All right, so let's start. Let's start with the inside. So let's first start with checking the inside, where R is less than A. Okay, so A is all the way to the edge, and we want to check a small region right before that, or any region before that is R. Okay, so that's what we're looking for here. All right, so let's set it up. We're going to use Gauss's law for the electric displacement, and we're going to get two integrals, 0 to pi, 0 to pi. We got dielectric r squared sine theta, this is Jacobian, d theta d phi. That's the left side. Now the right side is q free and closed. We're already going to put it in integral form, right? So we're going to do this q, but we're already going to represent it as integrals, and we're going to get three integrals because it's the volume. 0 to 2 pi, 0 to pi, and here is always the integral that causes the most problems. Let's do it in another color. 0 to r, because we're inside right now. So the distance that we're trying to cover is less than a. It goes all the way up to r. All right, and then this would be the bound. The only thing it's bounded by is the rho naught. Okay, that's the free charge. So this is the only thing that's free in that space. R squared sine theta dr d theta d phi. Okay, this is Gauss's law with all the integrals in place. All right, so let's solve it, and let's kind of do it in one step. All right, so this side we know is going to be, let's do it in two steps. We got d is 4 pi r squared. That's going to be from this side. Okay, and over here we're going to get, let's say we got 4 pi for the solid angle. Rho naught is going to come out, and the only thing we're going to have to integrate over is the r squared dr. So we're going to get r to the third over 3. Okay, and we're going to put the answer here. If we put this underneath on this side, we cancel out the 4 pi, r squared goes away, and we're left with the dielectric rho naught r over 3 in the radial direction. Okay, so we're in a sphere, so we're always going to be in the radial direction, or the linear isotropic homogeneous dielectric allows us to just look at the radial direction. And we're going to say this is inside, where r is less than a. Okay, now that we have d, we can plug it into our formula for potential and get the potential for the inside. All right, so now let's plug that into D. We get another color here. Let's see. All right. So we have potential is going to equal negative, right? If we're inside, then the potential always starts from the outside and goes towards the inside. So if we're somewhere in here already, we're going to start from the surface of the sphere inward. So our final is going to be R, and our initial is going to be A. So we're going to start from here, which is the shell, and we're going to work our way in until we hit R, some length R there. Okay? So remember that potentials work from the outside in, and inside here we're going to have the electric displacement of the inside over epsilon. So we got rho R over 3 epsilon. Okay, and this is dr. That is the differential length. It's an increase in the radial direction. All right, so solving this integral, and also since we're inside, we got to change this to represent what the dielectric could be in the inside, since we're dealing with a dielectric material. So we only got to do the integral of r dr. So that's going to be r squared over 2. The 2 is going to be multiplied by the 3. Okay, so we got, let's keep the minus outside for a second. We're going to take out the rho naught. We're going to take out the 3, and we're going to change this E, the epsilon, to KE epsilon naught. And so then the R integral, we evaluate it, and we're going to get r squared minus a squared over 2. I'll just put the 2 over here. So the 2 is going to be multiplied with the 3. And I'm going to take this negative and multiply it in, so that way I can flip these two around and I could just have a positive value. So the potential inside, right, where R is less than A, is going to be all of this. I'm just going to rearrange it, put the negative inside. So I'm going to have rho naught over 6, right, these two combine, KE epsilon naught, and then we have a squared minus r squared. Okay, this is the potential inside. Okay, so where do we, okay, here. So all of this for the potential inside. So we know that the potential could be represented with dielectric displacement, and we found that using Gauss's law. We used the charge-free volume bound, and solving for that, we got the dielectric displacement on the inside, which is what we needed. We expressed epsilon with KE epsilon naught, because we're inside the dielectric, and then that's it. So now let's do the outside. Right, so we had the inside, now let's do the outside. Okay, outside is R greater than A. All right, and so we're gonna use, again, this expression for the potential. Again, we're gonna need D, which is the electric displacement, and so let's do that. We're gonna use Gauss's law again. So we're gonna have two integrals, 0 to 2 pi, 0 to pi. We got D, and then we got the Jacobian, d theta d phi, equals, now we're gonna do the charge free enclosed, and the only thing that's gonna change is the most important thing, which is what everyone usually messes up on, which is what I used to mess up on. So this integral right here, the r, the radial integral, is always the one that messes things up. Now that I'm on the outside, this integral here is going to go from 0 to a. Okay, 0 to a, and there's free charge there, and then we put the Jacobian, r squared sine theta dr d theta d phi. Okay, so watch out for these limits here. Now let's solve it just like we did with the other one. We have d is equal to, I'm already going to put this 4 pi squared underneath, so 4 pi squared, right? And then all this answer is going to go on top. So we're going to have here 4 pi from the solid angle. We're going to have rho naught, and then from the integral we're going to have r squared, so we're going to get r to the third over 3. Okay, we're going to get r to the third over 3, and we'll replace it with a. So we're going to have a to the third over 3. All right, and these cancel out, and nothing else cancels out, because now it's a ratio of the outside shell to some distance r outside. And so our final answer is going to be rho naught a to the third over 3r squared in the radial direction. Okay, this is for the outside, where r is greater than a. Okay, now that we have that, now we can use the potential expression and plug in what we got for d. So again, like before, we have the potential, and let's write out negative integral. So now we're outside, okay? So let's say that we are somewhere out here, okay? All the way here is a distance of r. A is at the shell, okay? And when we do potentials, we're coming from the outside in. And so like the other example up here, since we were inside, we went from A to R, which was inside. But now R is outside. And so we have to come from the outside, like further outside. So some infinity value all the way to R. That's what we're integrating over. And so our integral here is going to look like this, infinity, and then the final position is R. So we started with all the way out here at some initial infinity value, and then we came in towards the R. Okay, and then we're going to write our electric displacement for the outside, and that's going to be rho naught a to the third over 3r squared, and this epsilon goes in there. Okay, and this is dr. Right, so now this one is different. This epsilon here is different from this one in here, because in the inside you have to express the permittivity of the material, of the dielectric, when you're inside with these values. But when you're outside, remember that when you're outside, chi is equal to 0. And so if this is equal to 0, then KE is equal to 1. KE right here will be equal to 1. So this, I'll go ahead and write it out. Let's do, okay, so we'll take one more step. We'll do negative, let's see, we got negative, we could take out rho naught a to the third. Okay, let's take out 3, and we're going to change this epsilon to chi ke epsilon naught. But this epsilon, this KE is equal to 1. Okay, so it doesn't, doesn't affect. What we have left in the integral is going to be infinity to r to the -2 dr, right? Because r squared was on the bottom, just put it on the top. And so we evaluate this integral. All right, so evaluating, let's write everything on the outside. A to the third over 3 epsilon naught. Now we don't have a KE. And if we do this integral, we're going to get, add 1, we're going to get -1. So we divide by -1, so we're going to get -1 over r. Evaluate it from infinity to r. Okay, and then what we're going to get from that, let's see. Let's just continue with this color. I'm going to leave the outside. Rho naught a to the third, 3 epsilon naught. And on the inside here, after evaluating this, we're going to get -1 over r minus a minus, so it's plus 1 over infinity, which is 0. And this negative and this negative are going to cancel out. So we're going to be left with the potential outside is going to be rho naught a to the third over 3r epsilon naught. Okay, and this is for the potential outside, where r is greater than a. Okay, good. So let's see, we found now the potential outside. Okay, and then we have one more thing to find, which is the total potential. And it's a little confusing because you can't just add the inside potential and the outside potential. You'd be wrong. And so I'll show you now in the next video. I'm gonna make another video why you should never do that, and how we're gonna find the total potential, which is the last thing, okay?